Dear students, continuing with our lecture series on organometallic compounds, this is our third lecture, and in this lecture we will discuss how organotitanium compounds they are used in organic synthesis. And in the present lecture we will deal mainly with the titanium tetrachloride. As you know, titanium belongs to first row of transition metals, and the electronic configuration for titanium is 3d2 4s2, and the common oxidation states in which various titanium compounds they are seen, they are plus 2, plus 3 and plus 4. The advantages of using titanium is that titanium is highly resistant to corrosion. So there will be no corrosion in case of titanium compounds, and therefore no side products there will be formed during the reactions. Then they have highest strength to weight ratio for any of the metals. And titanium is as strong as some of the steels which are known in the commercial sector. This is seventh most abundant metal, and as you know, the Boeing 737 Dreamliner, it has 15% of the titanium metal being used for its manufacture. And among the various titanium compounds, TiO2, titanium dioxide, is commonly used in paints and in the sunscreen. Titanium metal is also used for surgical implants, and the titanium oxidizes immediately on exposure to air, forming passive oxide coating, and the remaining part of the metal remains unreactive once the oxide has been formed. As far as organic synthesis is concerned, three common type of complexes which are used in organic synthesis, they are titanium tetrachloride TiCl4, titanium tetraisopropoxide having this structure, and titanosyne dichloride where two atoms of cyclopentadiene they are attached to titanium along with two chloride ions. And out of these, the most common one is titanium tetrachloride, and some advanced reactions in organic synthesis have been achieved using titanium tetraisopropoxide and titanosyne dichloride. So we will discuss these complexes one by one in different lectures, and in the present lecture we will discuss mainly TiCl4, how it is used in various functional group transformations in organic synthesis. Uh, TiCl4 is mostly used in combination with a tertiary amine, and this reagent system has been used in many types of organic functional group transformations. And most common among these is condensation reactions, and out of those aldol condensation and related reaction in organic synthesis, they are used for preparing different types of enolates which react with each other to give us various types of products. For example, if we use benzaldehyde, which is a non-enolizable keto aldehyde, with diethyl malonate, that is this diester, in presence of titanium tetrachloride and pyridine, uh, this will undergo Ovengel type condensation product, wherein two hydrogens from this methylene group and oxygen from this group will be removed as water, and this carbon oxygen double bond will be converted into a carbon carbon double bond, and the product formed is in 97%. So this is a very important common reaction which can be achieved using this tertiamine TiCl4 as the reagent. Then TiCl4 triethylamine can also be used for aldol condensation reactions. For example, if we take propionephenone and benzaldehyde, and you can see that one of the carbonyl group is non-enolizable. So here no acidic hydrogen is present in this carbonyl system, whereas this carbonyl system is having hydrogens present at this carbon, which can be acidic carbons because of the presence of this carbonyl. And because of this, a carbanion will be generated at this place, which will add to the non-enolizable carbonyl compound to give us aldol condensation products. And the beauty of this reaction is that here the product is formed with syn stereoselectivity. 95% of the product is formed where both these groups, methyl group and hydroxyl groups, they are syn to each other. So syn stereoselectivity is more as compared to anti-stereoselectivity in these types of titanium tetrachloride catalyzed reactions. Then TiCl4 and tertiabutylamine can also be used for collision condensation. For example, these types of diesters in presence of TiCl4 tributylamine using trimethylsilane triplet as catalyst can be used for collision condensation, wherein one of the ester group will act as a carbanion at the alpha position, and that will attack the carbonyl group of the other ester group with the removal of methoxy group from here. So methoxy from here and H from here, this will undergo cyclization to give us these types of uh, alpha carbomethoxy ketones as the product. Similarly, we can have open chain esters where both the esters which can be used, they are different from each other. So in this type of ester where this may not be having the enolizable hydroxyl group, enolizable hydrogens present. So the carbanion will be generated in this ester, and this will add to the carbonyl group of the other ester to give us these types of collision condensation products. Then non-enolizable aldehydes like benzaldehyde, they can also react with alpha beta unsaturated carbonyl compounds in the presence of same reagent TiCl4 and triethylamine, and this will undergo Baylis-Hillman type of products they are formed. So here what happens is the uh, TiCl4 will add to the carbon-carbon double bond, and then that carbanion generated from the reaction of this alpha beta unsaturated carbonyl compound will react with the non-enolizable aldehyde to give us these types of condensation products, wherein Baylis-Hillman type of products, they are formed in 80% yield in the present case when we are using 4-nitrobenzaldehyde as the non-enolizable. Then this TiCl4 triethylamine reagent can also be used for the dimerization of esters having methylene groups present. So, for example, this methyl phenyl acetate, when reacted with TiCl4 triethylamine, this undergoes dimerization to give us two types of products, either DL product or meso product is formed. But stereoselectivity is more in the formation of DL isomers. So 99% of DL product is formed, whereas 1% of meso product is formed. The mechanism basically is that in the first instance, this methylphenyl acetate interacts with TiCl4 and triethylamine, and the negative part of this TiCl4 adds to the oxygen of the carbonyl with the elimination of H from here, and a carbon-carbon bond is generated at this point, and we will get this type of intermediate with the removal of triethylammonium chloride, that is Cl from TiCl4 and H from methyl phenyl acetate, to give us this type of intermediate. And this intermediate will then again react with another molecule of methyl phenyl acetate, and this methyl phenyl acetate will attack carbon carbon double bond with the removal of TiCl3 from here to give us either DL isomer or meso isomer. But majority of the product formed is DL isomer of the dimerized product will be formed. So oxidative coupling of this intermediate in presence of second molecule of methyl phenyl acetate will take place to give us the desired. Then the uh, amino esters like this can be synthesized from the cyclization of these types of shift bases, or these will undergo intramolecular cyclization in the presence of TiCl4 triethylamine to give us these types of uh, pyrrolidine carboxylates as the product. So basically, there is a mistake. It should be B, and this A should be over here. So uh, gamma amino esters are these ones, and these are 2-aryl 3-pyrrolidine carboxylates. Then this same reagent TiCl4 triethylamine also interacts with carbon nitrogen double bonded compounds, where the substrates, they are having acidic hydrogens present on the system having carbon nitrogen. So because of the presence of this carbon nitrogen double bond, the hydrogens present on this carbon, they are acidic hydrogens. And in the presence of such acidic hydrogens, these type of shift bases, they give us heterocyclic products like pyrols in 81% yield, when the R is also a phenyl group. As far as mechanism of this reaction is concerned, because these hydrogens, they are acidic in nature, so the triethylamine abstracts one of the hydrogens from here like this. With the removal of this hydrogen, this will form a carbon-carbon double bond, and this bond will coordinate with the TiCl4 with the elimination of one of the halide ion, and we will get this type of intermediate. And then either on heating or even at room temperature. This bond is very unstable, and this will dissociate uh, in such a way that this type of free radical is formed during the reaction. Then two such free radicals, they will combine with each other to give us these types of carbon nitrogen double bonded compounds, which will undergo cyclization like this because of because these hydrogens, they are acidic in nature, they can be easily removed by triethylamine. So this will lead to the formation of a carbon carbon double bond. Uh, this carbon nitrogen double bond will attack at this place with the movement of hydrogen from here to this nitrogen, and this type of intermediate will be formed. In the next step, one more hydrogen will be abstracted by the base from here, and cyclization will lead to the formation of heterocyclic compound, that is 2,5 disubstituted pyrols. They will be formed as the product with the elimination of these prime derivatives. So these are the references which have been used for preparing this reaction, in addition to the references already given in each slide from where the examples have been taken. Thank you very much.